Hi guys, so now we move to part 4, chapter 5, magnetic circuit. Learning outcome for this topic, the first one is students should be able to analyze the series parallel magnetic circuit, and the second one is students should be able to analyze the series magnetic circuit by given the Ni and you have to find the phi. Okay, now for series parallel magnetic circuit. Okay, so we have to handle using the sum of flux principle or KCL. Okay, this is example 7 to discuss for the series parallel circuit. Okay, this core is cast steel. Okay, determine the current that established and air gap flux Fg is 6 times 10 power negative 3 Weber. Neglect the freezing. This is the dimension of the core uh, and the length, okay, for each part. Okay, so we have to calculate, okay, the current. What is the current injected here? Okay, with the number of turns is 200 turns. Okay, so this is the solution. Okay. For A gap, okay, B equal to phi over A. Okay, we know the phi and the area is, so we get the B is 0.3 Tesla. From B we can calculate H. Okay, H equal to B over mu, and the answer for H is 2.388 times 10 power of 5 ampere turn per meter. Okay, now we have to analyze section by section. For section AB and AD is for the is similar or share the same flux. Okay, flux with the A gap. So the B is 0.3 Tesla, and we have to refer to BH curve to see the H, okay, for this core. Okay, so the H value is 250 ampere turn per meter. Then we can use the Ampere's law for loop 2. Okay, summation of Ni equal to summation of Hn. Okay, so summation of we know that summation of because there is no, for this loop 2, no Ni, meaning here no injection current and coil here, so Ni equal to 0. But when we know the summation of HL, okay, summation of HL is HABLAB plus HGLG plus HCDLCD minus HDA LDA. Okay, from here, when you calculate here, then finally we can get the HDA. Okay, the HDA value is 925 ampere turn per meter. Once we know the H, we can find the BDA. Okay, BDA is 1.12 from the BH curve. Okay, so when we know the flux density, we can calculate the phi for the for part D to A. Okay, so phi 2 is BDA times A. Okay, so BDA is 1.12 times A is 0.02. So we get the phi for the phi 2. Okay, phi 2. Okay, now we know the phi 2. Okay, and phi 3. Phi 3 is the flux across the gap. Then phi 2 is the flux flow through the DA section. So phi 1 is the summation of phi 2 plus phi 3. Okay, so the phi 1 is the total of phi 1 is 2.84 times 10 power of negative 2 Weber. From here, phi1 is actually cover the section of DEA. Okay, so we can calculate the flux density for DEA section is phi1 divided by A, and we get 1.42 Tesla. Then after we know the B, then we refer to the BH curve to get the H. So the H value is 2125 ampere turn per meter. Okay, after we know all the H value, so we can do analysis for loop 1, okay, for ampere law, and I equal to HDEA LDA plus HAD LED. Okay, for loop 1, we only see HDA and HAD LED. We cannot see HAB gap and so on because that one in the other loop. So the total, the summation of NI is the summation of HL. So we can get the value of HL is 929 ampere turns. To get the current, okay, we have to divide by the number of turn 200. So the current inject in the coil is 4.65 amp. Okay, so we can refer this BH curve to answer this question. Okay, now we look at the converse problem. Given Ni and we have to find the resultant flux. Okay, for the case of core of one material and constant cross section, this is straightforward. So easy to get the answer. But for circuit with two or more sections, the process is not so simple. Before finding H in any section, you need to know the flux density. However, in order to determine the flux density, you need to know H. To get around this problem, we need to use try and error method. Okay. Okay, for example, 8. Okay, this is the simple magnetic circuit. Only one material. Okay, and one coil. Okay, so the number of turn is 25. The current injected is 10 amp. Determine the flux. Okay, this is cast steel material. So from here we know the summation of HL equal to summation of Ni. So H equal to Ni divided by L. Okay, we know the H is 1250. Then from here we can refer BH curve. Okay, BH curve, then we will get the value of flux density 1.25. When we know the flux density, we can calculate the phi by using B times A. And the answer for the flux value is 1.24 times 10 power of negative 2 Weber. Okay. But for example 9, okay, so we have now two elements. Okay, we have the core, cast steel, and also we have a gap. So given Ni is 1100 ampere turn, determine the flux in the core. Okay, so this the cross sectional area is 0.0025 meter squared. Okay, this is the dimension. So what I have to do is, firstly, initially we have to guess. Okay, assume 90% of the MMF appear across the gap. Okay, when we apply MMF is 1100 ampere turn, 90% is 1990 ampere turns. Hence, the Hg equal to 0.9 and I over L equal to 4.95 times 10 power of 5 ampere turn per meter. From here, we can calculate the B, okay, is 0.62 T. Okay, so the first trial one. Okay, since the area of the steel is the same as the gap, okay, the flux density is same. No fridging, we assume no fridging, we neglect the fridging. The B is 0.62 T, and from BH curve, H equal to 400 ampere turn per meter. Then we use the Ampere's law, summation of Ni equal to summation of HL, then we get total is 1070 ampere turns. Okay, this answer is we show here is 2.7% lower than the given Ni of the question is 1100, but we just now we just guess that MF across the gap is 90% of the MMF. So but this is acceptable because it's the error is just 2.7%. Okay, next example 10. Okay, this is one of the past year question I would like to discuss to you. Okay, as shown in figure Q4b, a rectangular iron core has a mean length of magnetic path of 80 cm and cross-sectional area of 4 cm squared. The iron core relative permeability is 1500 and a gap of 3 mm cut in the core. Okay, 3 coil carried by the core have number of turn, and A is 450 and B 700 and C is 500. So this is an A and B and C number of turn. And the respective current IA is 1.5 M, IB is 3 M, IC is 4 M, with the direction of current flow as shown in the figure. Determine the flux in the A gap and sketch the direction of the flux. Okay, the mu naught permeability of mu naught is 4 pi times 10 power of negative 7. So firstly, what you have to do is you have to sketch. Okay, when the current flow in this coil. Okay, so what is the direction of the flux? Okay, so we can use the right hand rule, okay, to see the direction of the flux. Okay, for the first coil here, this is the first coil. We can see, okay, when the current is entering this point, okay, so the flux, okay, is up, okay, is upper. Okay, for the second one here, okay, when the flux, okay, enter here, okay, the current enter this coil, okay, at this point, okay, the flux is flow, the direction of flux is down, okay. And for the C coil, okay, when the current is inject here, okay, the flux direction is at the right side, okay. So from here we can see that for coil 1, coil A, coil B have the same direction, but for coil C has the inverse direction. So we can add on this Ni and Ni for A and Ni for B, but for Ni for C we have to minus. Okay, so this total EMF Nia plus Nib minus Nic. Okay, so we got 775 ampere turn. Then we can use reluctance for the A gap equal to L divided by mu naught A. Okay, then we got this reluctance for the A gap. Reluctance for iron path. Okay, the total reluctance is add on this reluctance from A gap and iron path. This is the total reluctance. So the flux, okay, we know the equation like the Ohm's law. The flux equal to mmf divided by total reluctance. The total mmf is 775 and total reluctance is 7.02 times 10 power of 6 ampere turn per Weber. So from here we can get the flux. at the air gap value. Okay, for exercise 4, this is the sheet steel. Okay, so you have to determine the current established in the air gap when the flux is 5 times 10 power of negative 3. Neglect the fridging. Okay, then you have to submit the exercise 4 in the empty assignment. Thank you.